So continuing the morning's theme of major algebraists of our time, Professor Parimala is the Arts and Sciences Distinguished Professor of Mathematics at Emory University. And among her many honors, the one particularly relevant to the motivation for this conference is her plenary address at the 2010 International Congress of Mathematicians.
Thank you, Ravi, for your kind introduction. And I'd like to thank the organizers for giving me this opportunity to be part of this celebration. Okay, so I asked whether I could lecture on the board and how good are your boards, and your secretary said, I'm not sure, but I'll send you the picture. So I said it was very good, so let me try. So the title of my talk has Hasse principle in it. The key idea, the key motivation is always you're looking at polynomial equations or rational numbers or algebraic number fields, and you're trying to look for solutions. And the first order of difficulty is to find solutions locally at completions. Okay, this is the idea of Hasse principle. And once if you are able to find solutions locally, then you try to revert back whether you can solve the equations over your given number field. This is the basic idea of Hasse principle. Maybe I'll motivate by the very first example from which the very nomenclature Hasse principle started evolving. This is the so-called Hasse-Minkowski's theorem. So let me just give the setting. Suppose Q is so we are over Q, and Q is a quadratic form which is given by over Q, which is given by AI xi squared, AI in star. And we would like to determine when this quadratic form represents zero non-trivially. That means whether you can find solutions in Q lambda 1, lambda 2, lambda n, not all zero, such that this form such that summation AI lambda squared equals 0. This is called the isotropy of the quadratic form. Whether it represents zero, it is called isotropy. And so if you're looking for isotropy for this quadratic form, you can easily clear the denominators and you can assume all the AIs are in Z. And you can also remove the common factors between AIs. And so that's what, so if you do this, you call it Q is a primitive quadratic form. Primitive. That means the AIs are integers, there is no common factor between them. And you try to look for some necessary conditions for this to represent zero non-trivially. And one obvious condition is Q is contained in real numbers or reals, which should represent zero non-trivially, is the same as its indefinite quadratic form. That is, there is a change in the sign of AIs. That's the necessary condition. And you have more conditions, in fact, in terms of congruent solutions. So you can look modulo n, because the form over Z will be, if you can solve over Z, you can solve, if you can solve over Q, you can solve over Z, you can solve over Z, you can solve over mod n. So mod n solutions are necessary for this quadratic form to represent zero non-trivially. And then once you have this necessary conditions, you have this theorem of, this is the theorem of Minkowski. That Q is a primitive form as before. Q represents non-trivially. Q is, maybe I can use the word isotropic. If it represents, if it is indefinite, that is, there is a change of sign in the coefficients, is a necessary condition, and has congruent solutions mod n, non-trivial congruent solutions mod n. For every integer, all integers, suppose there are congruent solutions plus indefinite, that means that this form represents zero non-trivially. This is the fundamental theorem of Minkowski. And so this so what does it have to do with what I said in terms of completions? This was translated into the following theorem, which is due to Hasse-Minkowski. This is a translation into completions from mod n solutions and little more. So here, so we need to introduce the objects, the local objects which are completions. So over Q, you have this following complete fields QP, which contains Q for every prime P. These are the periodic completions. How are they defined? You define a norm on this field by using this this function VP. VP of you take a rational number, write it as p power n times a by b, where p does not divide a, p does not divide b, and a and b non-zero, and then define it to be n. How much divisibility it has in terms of p, that defines a norm on this q, and this is the completion of q with respect to the norm induced by this so-called discrete valuation VP. Okay, so this is the these are the completions for every prime, and so you call omega q this set of all VPs for all primes, and also the infinite prime, which is given by the absolute norm. The absolute value gives a natural metric on q, which when you complete you get the field of real numbers. So this together, so you have this local data, and you have this set of overfields containing q, namely the p-adic completions with respect to the p-adic metric, and the field of real numbers for the Archimedean valuation, the set of completions, and then Hasse-Minkowski's, and also, so this is the case for the number fields, and you can take any finite extension of q. These are the so-called number fields. You can do the same thing, extend this to the places of k, which are simply the extensions of these valuations to the finite extension k of q. And you can talk of completions of the number fields, and Ms. Hasse-Minkowski says that a quadratic form over a number field, quadratic form over a number field is isotropic. Isotropic if it is isotropic over all completions. Isotropic over KB for all places you take the completions. If it admits a zero non-trivially over the completion, then it has a zero over K. And what is the connections between these completions and the congruent solutions? It's precisely the statement that congruent solutions mod n for every n implies solutions in QP for all p. Okay, that's the translation for Q. So this is exactly, things were happening at the same time, early 20th century. So Minkowski obtained the solution, Hasse was there, and Hensel was formulating his entire theory of complete fields, lifting solutions, and so on. They all came together, and so that is how this translation was obtained from here, and little more arithmetic. And so you have this complete theorem that to test for solutions of a quadratic form or a number field, it's enough to check it locally at all completions. So this possibly could be thought of as the origin of Hasse principle. So now it is a big area of research, namely instead of quadratic forms, so you can translate it into a statement on Hasse principle for quadrics. This is just so a quadric is simply defined by summation ai xi squared equal to 0. So if it is I less than or equal to n, it is in Pn minus 1. So suppose n is at least 3, it defines a number of variables as at least 3, it defines a smooth projective variety. So this can be thought, and isotropic for quadratic form is just the rational point on the quadric. So the translation is that the quadrics satisfy Hasse principle. So now there's a big question, big research on the topic of Hasse principle for varieties over number fields. Looking for solutions of equations over number fields is an all interesting topic of all times. And this is one area where you look for at least one solution. So this Hasse principle method, now we know there are obstructions to Hasse principle and study of obstructions in all directions, trying to locate all obstructions. These are all the big areas of research, which I'm not going into deeply, but I will just want to mention one particular direction in which there has been very good progress about Hasse principle, even classically. Okay, so these quadrics are examples of the so-called projective homogeneous spaces. Projective homogeneous spaces. So what are these projective homogeneous spaces? So G is a connected linear algebraic group. Linear algebraic group. In the last lecture, we heard about principal homogeneous space. X is a variety defined over, it could be over any field F. X is a variety defined over F. and X has an action by G. So G acts on X, and then it is transitive. Just put it in quotes. That's called a homogeneous variety. Transitive means, of course, over the F bar points of X, there is the action of G on X, G F bar on X F bar is transitive. That is the notion of transitivity. Then such a space is called a homogeneous space, and the projective homogeneous space in addition means X is a projective variety. Okay, so a projective variety on which group acts transitively. Okay, the action is algebraic. This is the sense of Zariski sense. These are the projective homogeneous spaces. If you want to think of it more concretely, these are over the algebraic closure. These are all the so-called flag varieties, and so these are twisted forms of flag varieties in the notion of how Mercury explained it. These are forms for the flag varieties. See, these are the projective homogeneous spaces. Of course, one example we have seen is quadrics are projective homogeneous spaces. If Q is Q equal to 0 is the quadric Q defined by this, then Q is homogeneous under the action of SOQ and the special orthogonal. So we are in the domain of projective homogeneous spaces when we looked at quadrics. It's a special classes of varieties. So if you take projective homogeneous spaces, then we have the following beautiful theorem of Harder, which says that theorem of Harder says that Hasse principle holds. We say Hasse principle holds if a variety locally admits a point, it already admits a point over the field, and a class of varieties we say satisfies Hasse principle. Every member of the family satisfies Hasse principle. So he proves that Hasse principle holds for projective homogeneous spaces, and connected linear algebraic groups. Linear algebraic groups. So this gives a complete class of varieties which satisfy Hasse principle, of which the quadrics is one particular example. Okay, so of course there are some more interesting theorems about Hasse principle. The so-called Hasse principle for principal homogeneous spaces for some special classes of groups called semi-simple simply connected groups. That's the so-called Hasse principle conjecture of Sayre, and that was also settled, and I'll come back to it at the end if I have time. But also abstractions are quite well understood for homogeneous spaces and the groups over number fields. Over general varieties, it is still so many open questions. At least complete set of abstractions in terms of the so-called Brouwer-Manin abstraction has been quite well understood for homogeneous spaces under connected linear algebraic groups. I'm not going into the full list of the references, but it is a very interesting topic of its own, with still some little open questions at the end. But I want to, at present, move on from the classical setting to what is happening in the last 2 decades and some kind of progress in this direction. Okay, so towards that, I'm branching off. So I'm going to look at the following class of fields. So we looked at number fields, and in the process, we looked at periodic fields, and we had results about Hasse principle and so on. So one would like to look at function fields to start with. X is a curve. Function fields in one variable over a base field, either say periodic field or K is a number field. So these are interesting examples to pass from. Instead of taking varieties over K, you have a parameterized class of varieties and so on, and you can look for varieties over such fields, call this F, over such fields, and you can look for some method of determining when varieties or homogeneous space or whatever admit rational points, knowing what is the local data is the question. So maybe these questions are not per se extending the case of number fields, but they have very nice arithmetic consequences for such fields. I'll just begin with one motivation of this kind of extension of Hasse principle questions. The example, once again, is my favorite of quadratic forms. Suppose K is a number field. So you may look at see totally. I want to avoid ordering. It's totally imaginary. So you can just have in your mind q root minus 1 as an example. And then you take function field in one variable over this number field. You can have q root minus 1 t rational function, this as an example. So the question is the following. So does there exist an n, however large it is, such that quadratic forms in at least n plus 1 variables beyond this n represents zero non-trivially. That is isotropic, zero non-trivially. This is the question, that if you take such a field q root minus 1t, one natural question is, if you take large enough dimensional quadratic form, does it always represent zero non-trivially? Okay, this is just a very natural, interesting question to ask for such a simple field like q root minus 1t. And what would it lead to if we had some kind of a Hasse principle? So I'll explain. So unlike in the case of number fields, we had some kind of given set of places, you can't look for others. Okay, there's natural. Here we have to define what are the completions you're going to look at. And you can look at all completions, it doesn't matter. But I would look at so-called divisorial discrete valuations, divisorial. So I don't want to go into technicalities, but just to say it quickly, you have a curve over K, and you have this integers over number fields, ring of integers. You take regular proper models, and you take codimension 1 points here, and look at all the discrete valuations centered at such codimension 1 points for all possible models. Okay, some kind of geometric thing going on around it. So these are the divisorial discrete valuations. So main important point of the divisorial discrete valuations is, for every v in omega f, what are the residue fields? Okay, look at the completion fv, completion of omega f at v, and the residue field kappa v. So you have a complete discrete valued field, you have OV mod pi v, the associated residue field associated with the valuation, this kappa v. Okay, this in this case it happens to be a global field. Whatever v you choose, either it is a finite extension of your number field, or it is finite extension of fqt. It's always a global field. You have a lot of information on arithmetic over the global field. You have the class field theory available. For instance, Hasse-Minkowski's theorem, every 5-dimensional quadratic form is isotropic over this field. From this, it is an easy way to conclude that when you pass from the residue field to fv, this is Hensel's trick, that if every 5-dimensional quadratic form here is isotropic, every 9-dimensional quadratic form is isotropic over fv. Okay?
Could I ask why you're restricting in the first case to totally imaginary?
Because I don't want to look at real orderings to start with.
You know what the answer is?
That is infinite, right? You cannot limit the number of variables. You always have forms 1, 1, 1, 1, which is anisotropic. So I want to look at some finite U invariance kind of a thing. So those are when the field has no orderings. So K is the total, that's what I didn't mention. K is a totally imaginary number field. Every 5-dimensional quadratic form is isotropic because locally over the completions, every 5-dimensional quadratic forms are isotropic. You know the unit structure, it's very easy to determine that 5-dimensional quadratic forms are isotropic over a local field, completion of Q at P. And therefore, Q root minus 1, if you take, then every 5-dimensional quadratic form over a totally imaginary number field is isotropic. Okay, the same with respect to global fields. So you have that 5-dimensional quadratic forms are isotropic. So which would imply that it's an easy passage that 9-dimensional quadratic forms over the completions are isotropic. Okay, this is an easy switch. So this is okay. So suppose in my dream, suppose Hasse principle exists. Suppose Hasse principle holds. Not necessarily for all forms, for forms of dimension at least 9, large dimensional. Okay, if this happens, then this would imply that every 9-dimensional quadratic form, dimensional quadratic form over f, which is function field k of x, has a non-trivial 0. Non-trivial 0. Not only finiteness, but you will get that every precise estimate that 9-dimensional quadratic forms over q root minus 1p has a non-trivial 0. We can take it as an challenge to see many young people here. That is a very interesting question, but we are nowhere near the solution of this question. And we do not know Hasse principle holds. We do not have great success in this direction. However, so there is one thing where one can say something. Is we have some success is that, so I have how much more time? 10 more minutes or no, 20 minutes. So I have, suppose K is a periodic field, local situation. Instead of a number field, let me take a periodic field, and F is the function field of a curve or a periodic field. Here there is some really good progress on questions in this direction. And the first one I want to quote is the theorem. This is Kolyotkalin and myself and Suresh. So we proved that Hasse principle holds for quadrics or F. Okay, we proved Hasse principle for quadrics. Of course, we had the assumption that it is a non-dielectric periodic field. As a corollary, what do you get? So you have the same discussion for the residue fields. They are all going to be global fields or local fields, and so every 5-dimensional form, every 9-dimensional quadratic form or locally is isotropic. As a corollary, you get, because there is Hasse principle, corollary. So I'll call it every 9-dimensional form, 9-dimensional quadratic form or F is isotropic. That is, we call it the U invariant, the maximal dimension of anisotropic forms. We call the U invariant. The U invariant is 8. Okay, every 9, this precise result. This was an open question for decades, but it was settled earlier by myself and Suresh. But now we have an alternate proof, which is much sharper. It is just not for 9-dimensional forms. We have Hasse principle globally for quadratic forms of dimension at least 3 smooth quadrics. There is Hasse principle. Okay, so this is a very satisfying progress in the case of local fields and function fields of periodic curves. And then we also analyzed Hasse principle for principal homogeneous spaces. Where is the eraser here? And we discussed Hasse principle for many more homogeneous spaces, and we made somehow motivated by the number theory case and also encouraged by some examples like this quadrics, we ventured to make the following conjecture. So namely, but it is not a conjecture very analogous to the number field case, Hasse principle holds for projective homogeneous spaces under connected linear algebraic groups, algebraic groups over function fields of periodic curves, groups over function fields of periodic curves, So this was the conjecture which is very close to the case of number fields, and we worked out a few examples where it happened to be true, and so it was a while to make this conjecture. And so there were several cases of this. So this has been part of our trying to one of the problems we are interested in to solve, and there were some cases which were settled towards this conjecture. For instance, I said already quadrics, it is true, and all classical groups. This was settled by Suresh and myself, and also much before this Suresh, this result, the case of the groups of type A and 1, that is generalized Severi-Brouwer varieties, These are these examples of such spaces, projective homogeneous spaces. This was settled by Reddy and Suresh. Okay, so there is complete progress in the case of classical groups, but that's not the end of the story. There are the other most beautiful groups for which one doesn't know a solution. And so this is where it stood. And I wanted to say at this point that something which is really, really remarkable in this context, both in the case of the theorem of this I quoted for quadrics, Collier-Thelian, etc., the theorem for quadrics, as well as for the generalized Severi-Brauer varieties where it was proved already. The whole point was that the base field K, in the conjecture it is a p-adic field, but in the proof they never used that K is a p-adic field. The proof holds in general for any complete discrete valued field, no arithmetic attached to it, complete discrete valued field, etc., etc. So the conjecture was proved in this setting for those two examples, though for other examples of classical proofs, we did use the arithmetic of the residue field. Okay, it's just a weird question. Could the conjecture be true in general if you replace K, which is a p-adic field, by any complete discrete valued field? Could it be true instead? Okay, this is where the things started turning around. So this is the so-called semi-global field. This is simply the following. K is a complete discrete valued field. Example is a p-adic field, complete discrete valued field. And X is a curve over K, and F is K of X, function field in one variable. Function field in one variable. Okay, so this is such a field. F is called a semi-global field, and so our question was, could we possibly prove the conjecture in the more general setting of semi-global field? Since in the sporadic examples where we proved, it seems to be true, and this question seems to have a positive answer, and that's what I wanted to state. So this is the theorem of Gilles and Maxer. So Hasse principle holds for projective homogeneous spaces. For under connected linear instead of connected linear algebraic groups, if you take a general complete discrete valued field, you may have different characteristics coming in, and we do not want to deal with weird unipotent groups. So we just say under a reductive group or a semi-global field. So this is the main result. This is classification free. So namely, Hasse principle holds for all projective homogeneous spaces under reductive groups or any semi-global field. So I'm hiding something. There is some condition on good residue field characteristic. That is, you have a complete field, you have a residue field of K. So good residue field characteristic assumptions are there, which I'll not go into the details, but it is like in the case of, for instance, in the case of orthogonal groups and so on, you avoid the prime 2, maybe a little more, but this is the kind of assumptions we have. We had the assumption P not equal to 2 even in the other case of Collier-Thelian and our earlier result. So such kinds of residue field characteristic assumption, which is mild. So you have a complete solution to this Hasse principle question over semi-global fields. This is good news. And so I just want to mention a few words on what brought about this transformation into results coming out over semi-global fields and as well as function fields of p-adic curves. The starting point is the so-called patching techniques, which were introduced by Harviter, Hartman, Krashen, which I'll say a couple of words. So the so-called patching techniques exactly fitting into the setting of semi-global fields, patching techniques. Okay, so what they did was you take F as a semi-global field, which is a function field of a curve. You can assume it's a smooth projective curve or a complete discrete valued field. Suppose small k is the residue field, and you can think of a model for the discrete valuation ring, and you can look at the special fiber you can special fiber or little k for this model. You can assume that this special, by the resolution of similarities, you can assume that the special fiber is in good shape. It's the union of, it's a normal crossing device. That's a special, you can assume it is in good shape. So in this situation, they attached a finite set of overfields mu in some finite set. So instead of completions, they introduce some finite set of overfields. They are not complete discrete value fields. They are related to the geometry and arithmetic of this function field. This F nus are parameterized by the components of the special fiber as well as the nodal points of the special fiber. These are the things which parameterize the superfields. These are finitely many in number. That's the whole point. And then they give conditions under which, suppose Z is a variety over F. So they look at Hasse principle question, ZF not empty. If ZF nu not empty for every nu in that every nu in this finite set. So they look at this finite set of overfields and look for if locally over these overfields they admit a rational point, they have a rational point over F. So this is the discussion, and they prove something quite nice that if G is a rational group, that is rational means its function field is a rational function field. Okay. If you take a rational group, then this is true for not all homogeneous spaces, for projective homogeneous spaces. So Hasse principle in the patching sense. So I call this the Hasse principle for the patching sense. It holds. So if you admit rational points over this finite set of overfields, then you have a rational point over the given field. So this is the nice result for G rational. So this has been used in much of the work in this direction over function fields of periodic curves. But I will quickly mention what goes into this final result of Philip Gilles and myself. So there are two difficulties. First, we cannot use this. Even if you want to prove a Hasse principle in the patching setting, you cannot appeal to this theorem because reductive groups are not in general rational. You have all kinds of non-rational groups which have come into, which are proven to be non-rational. So you cannot use their results directly. So, and secondly, so these are some finite set of overfields. They are not complete discrete value fields. What is the connection to our question of discussing rational points over completions vis-a-vis this rational points with respect to patches? Okay, there are two different kind of questions to be answered, and I would just like to say that so first non-trivial step was to prove that Hasse principle holds in the patching setting for projective homogeneous. It's not readily available from Harbeta-Hartman-Krashen, but we prove it patching in the patching setup for projective homogeneous spaces. This is the one non-trivial job. And the second step, which I will say even much less, is how do you reduce from the local complete setting to the patching setting. This involves quite a lot of techniques from outside. I mean, outside in the sense, the so-called loop process. This input came from Philip Gilles, and that's how we saw that we could see the end to the tunnel. So this is the so-called theory of loop process, which is developed by Pianzola and Gilles. And some of the non-trivial results proved about loop process by Gilles, Chernuso, and Reistein. So these are the results from loop process, which enables one to reduce the question over completions to the one over patches. So this can be done, and you can do the work over the patches even though the group is not reductive. Together it leads to a solution of the original question that there is Hasse principle for projective homogeneous spaces or any semi-global field for any reductive group. Okay, you can delete the assumption reductive if you have a characteristic zero field. So you do get Collet-Thelins conjecture for function fields of periodic curves. So I have a couple of minutes, so I have few. Okay, I just wanted to mention a couple of words about comparison with the case of number fields. I quoted Harder's theorem, which settles the conjecture for projective homogeneous spaces under connected linear algebraic groups over number fields, and it uses in a fundamental way the so-called Hasse principle conjecture, which I mentioned, which is a Hasse principle for principal homogeneous spaces under semi-simple simply connected groups. It's a deep result of Hasse principle which goes into it, which Harder uses to prove his theorem for projective homogeneous spaces. Okay. However, in our case, when you move from function fields of PID curves to general semi-global fields, okay, Hasse principle in the setting of semi-simple simply connected groups is simply false. So you do not have a Hasse principle theorem for general semi-simple simply connected groups in the setting of semi-global fields. It's proven to be false. It's not too long ago. It was again the collaboration of Harbater, Hartman, Krashen, and CTPS. I mean, we are looking at these questions of Hasse principles, and we could get at even examples like SLD where it fails. Okay, so you cannot update it to in the general setting to a Hasse principle conjecture. And secondly, this proof of the theorem is completely classification free, and I want to say that getting a classification free proof of the Hasse principle conjecture for number fields is still a dream of a mathematician. We do not have it's all case by case, so it'd be wonderful to have even a classification free proof for the case of number fields. I'll stop here. Thank you.